Hello, everyone. So today we are talking about earth science. So what is earth science anyways? So let's start with the word science. Science is derived from the Latin to know, which is scientia. And currently, the way that we define science is to know through a certain process that we call the scientific method. And the scientific method is a systematic study of any subject through experimentations, observations, and then analysis. The textbook, the textbook is going to argue that the first step of the scientific method is to ask questions. I disagree. I think in order to ask questions about the environment and the earth, we need to first observe the environment or the earth. And through that, through those observations, we can make either qualitative observations using our senses, or we can make quantitative observations by taking measurements. These observations are often informally done, and we barely know that we're even using the scientific method when we're making those observations. For example, I might smell something rotting when I wake up in the morning. And the first thing I do is ask myself a question. I don't start making an experiment. I don't write a hypothesis. I ask myself a question. Is there a dead mouse in the kitchen or am I getting a sinus infection? Those would be two reasonable questions that I might ask myself. I might also step on the scale each morning and notice my weight is going down. I might ask myself, do I have cancer or is my diet and exercise finally kicking in? Those are questions that we make after we've made an observation. So this is a very, very important part of science and the scientific method that often goes overlooked, but it's simply to be aware of the observations and the environment, anything observation we're making of the environment that we make every moment of every day. And when you come to that realization, you can realize we're all scientists. As I said before, the textbook talks about the first step in the scientific method after making observations about the environment is to ask questions. Questions can be as silly or as realistic as you want because the scientific method has fail-safes built into it that weed out unreasonable questions. And the scientific method is to conduct research. Let's go with the dead mouse sinus infection question that I initially asked. I could easily do a cursory internet search from a reputable medical facility like Mayo Clinic out of Rochester, Minnesota, to see if the smell of rotting meat is a symptom of a sinus infection. A possible explanation for an observation and subsequent question that has been backed by research is called a hypothesis. So again, we're going back to that dead mouse sinus infection example. I might say something like, since it's the dead of winter and the air is really dry, I hypothesize that I have a sinus infection. Or maybe I made this smell observation, this very initial observation before I even asked the question. Maybe it's fall and we just had a cold snap and I hypothesize that there's a dead mouse under the stove. The next step in the scientific method is to design an experiment. So in the dead mouse sinus infection scenario, I haven't actually even left my bed yet, and I'm going through the scientific method in my head. So let's just say it's January, and my hypothesis is that this is a sinus infection. So when I'm designing my experiment, I want to use a reliable source to determine the types of observations that I might need to make. So for example, like I said, I would use my reliable source would probably be the Mayo Clinic. I might also make some other initial qualitative observations. So one qualitative observation would be like looking at the colors of my boogies, or a quantitative observation, I might take my temperature, just get up and go to the bathroom, take my temperature, and see if I have a fever, which is generally a sign of infection. And both of those are active indicators, just from my knowledge of science and biology, that my body could be fighting an infection. So if I were designing an experiment, however, I might start taking something like a fever reducer, like ibuprofen. I might start drinking extra water. So maybe instead of my usual 120 ounces, I might bump it up to 150 ounces every day. I might go to bed early. So instead of going to bed at 9:30 like I normally do, I would hit the hay at 8:30. And I would continue. So in an experiment, there's always a time limit, right? So I would maybe conduct this experiment for 2 days, so 48 hours, and I'd be continually making observations. I would be observing things like, do I smell this rotting smell on a regular basis? What color are my boogies? What is my body temperature? And then I'm also going to be kind of keeping an eye out for any new symptoms that the Mayo Clinic might recommend, like fatigue. So fatigue would be another sign of a sinus infection. So I'd keep track of this information in a notebook in my bathroom, just because that's where my thermometer is, and I might forget. In this day and age, you could also keep track of that kind of stuff on your phone. Your smartwatch keeps track of that kind of stuff for you. Boogie measurement, that one, I don't think smartphones keep track of yet. Now that I have 2 to 3 days of data, I need to make sense of all of this information that I have. So again, I have a list of how much I've been observing the rotten meat smell, how many days that I've been observing the color of my boogies, and the body temperature throughout the day as often as I can. What I've noticed, my observations in this analysis, is that my boogies are clear and my body temperature has been 98.6, and I actually didn't observe the rotten meat smell a second night, but it was observed when my husband rolled over in his sleep, and that's a suspicious observation in my analysis. In any scientific experiment, sharing the results is the final, and I would argue the second most important step after those initial observations and being aware. So when we look at communication, this isn't just about sharing the results of a perfect experiment. It's about sharing the initial observations and the research process that we used, the resources that we used to answer our question, and how we designed our experiment, and how we analyzed our experiment. All of that is incredibly important to share. Our research allows other scientists to try the experiment for themselves, resulting into the development of scientific theories. This also gives other scientists new ideas that they turn into their observations and then the questions that they come up with for their own scientific method. Maybe the initial observation of the first scientist is just slightly different than another scientist's observation. This could initiate a different line of questioning, and subsequently a different line of experimentation, and ultimately different results. Now that we understand how science works, let's look at the Earth. This is the Earth. The round on the left represents the solid part of the Earth, and that is uh, the study of geology. We refer to the rocks and mountains and ground as the geosphere, and the people who study it are geologists. Physical geologists study the Earth's composition and movements today, while historical geologists study the composition and movements of the Earth as and how they've changed over time. Among physical geologists are those who study the chemical composition of the Earth, while others study the physical composition of the Earth. So, with all of that, um, the chemical composition of the Earth, it might require additional knowledge. So, for example, in chemistry, or if they're studying the physical composition of the Earth, they might need to know the physics of how the Earth moves. We refer to all living things on, in, and around the Earth as the biosphere, and the people who study living things as biologists. On land, a plant biologist is called a botanist, and an animal biologist is called a zoologist, and scientists who study life in the oceans are marine biologists. This represents the air on Earth. We refer to the air on Earth as the atmosphere, and the people who study current weather conditions of the atmosphere as meteorologists, while historical weather conditions are studied by climatologists. The blue in this video represents the liquid on Earth. We all know that the ocean is not actually blue, it's just a reflection. However, from space it looks blue. And even just sitting on a boat, sometimes the ocean looks blue. So we refer to all the water on Earth as the hydrosphere, and that includes all of the solid, gas, and liquid water. So there's solid water in the ice caps and glaciers, and in Minnesota in the winter. And then there's also liquid water in the oceans, but also lakes, rivers, and there is water in the form of water vapor in our atmosphere. So the people who study the oceans, all the salt water on Earth, they are called oceanographers, while the people who study things like lakes are called limnologists. So freshwater, still bodies of water are limnologists. We also have people who study solid water, and they are called glaciologists. The Earth is also surrounded by the vast reaches of space, which includes the sun that keeps our planet warm enough to live on and have liquid water on Earth. It also provides UV radiation, which feeds our um, plants and keeps the photosynthesis going steady and strong. The moon is also out in space, and that affects our tides, which ironically our tides are affected in the middle of the continent, which is interesting. And there are also other planets and moons and um, even distant galaxies that are part of our space. And the scientists who study the space that surrounds Earth and the distant reaches of the universe are called astronomers. So, why is it so important to study Earth science? Well, everything on Earth is interconnected. So, things happening in one sphere influence other spheres. Now, humans make up a very small part of the biosphere, but we live across a huge part of the geosphere. We utilize the hydrosphere and the atmosphere. As with any system, there are benefits and risks to humans who are spread across a diverse landscape with diverse waters and diverse air. The biggest benefit that the environment provides are the resources for humans to live. Renewable resources are those that can be replenished within a human lifetime. Uh, so, for example, like less than 75 to 150 years. And we put 150 years as kind of a generational gap. So, you know, a father might tell his son to plant another tree so that generational history and story is there. Resources that are renewable include they provide us with food like pumpkins and sheep. They provide us with shelter like trees, clothing like cotton plants, or energy like the sun or water. Non-renewable resources, on the other hand, are replenished on a geologic timescale, so that takes millions of years. These resources also provide us with shelter, for example, steel beams in our bigger buildings, and energy like coal that we use still for electricity. They also help us store our food. So they might not provide us with food, but they help us store our food. So aluminum pop cans would be an example, or tin cans that we store our canned corn in. But they also provide a basis for our economic trade, like currency and fine jewels and those types of things. On the other hand, there are some places on Earth that are more prone to risk. For example, Southern California has a higher risk for earthquakes, but has a mild, temperate climate with a good growing season. Southwest Minnesota, on the other hand, has really fertile soils and few insects that can survive the harsh winters, but that also means we have harsh winters, and we're also prone to some pretty severe weather in the springtime also. As we continue through this lecture series, we'll take a pretty deep dive into geology, since the geosphere is where humans spend most of their time. But we're also going to very briefly touch on oceanography, meteorology, and astronomy. And much of the focus on this lecture series is going to be on kind of that human piece of of earth science, of how humans kind of interact with their this with space, but also the geosphere, the biosphere, the atmosphere, and the hydrosphere. So when you look at all that earth science has to offer and all of the possibilities within this field of study, which branch appeals to you most? Is it astronomy? Do you like studying the stars? Or perhaps physics that relates a lot to the study of astronomy? Maybe it's the study of geology and the rocks and the way that the ground moves. Or maybe it's the humans that live on Earth, or any of the living things that live on Earth. Maybe you really like to study the weather or past climates. What about studying the ocean and all of its mysteries? With both oceanography and meteorology, there's a heavy component to chemistry. So maybe you just like the study of chemistry and maybe you want to understand where it could be applied. Maybe you like to study the social sciences, which humans are part of the biosphere. And so the study of humans is technically a branch of earth science. And maybe within the social sciences, you want to study maybe managing or leading or educating students or people. Maybe you want to study how people express themselves, or maybe you want to study how they communicate. All of those relate to earth science.